Okay, buckle up. Today, we're diving into one of the most persistent, mind-bending questions humans have ever asked. One that has fueled countless hours of science fiction, but also sits right at the cutting edge of theoretical physics.
Hmm.
Can we actually travel through time?
It's a concept that really sparks the imagination, doesn't it? We've all thought about it as, what would we do if we could journey to the past or the future?
Oh, absolutely.
But moving beyond the fiction, what does the actual science as we understand it right now really say?
Exactly. And usually the conversation about the science starts and often ends with those famous paradoxes. But what are the underlying physical principles that even allow the possibility of time bending in the first place?
Mm.
What are the theoretical mechanisms and, what are the rules physics seems to impose? That's our mission today. We're doing a deep dive guided by a stack of sources on theoretical physics, unpacking what current scientific theories, particularly Einstein's relativity and quantum mechanics, reveal about bending time. The wild possibilities they permit, at least in principle, the fundamental challenges they throw at us, and yeah, the paradoxes that keep physicists up at night.
Right.
What does time travel even mean in a scientific context, according to these sources?
Think of us as your guides through this complex, but I think really fascinating material. I'll bring the analytical lens, sort of helping to synthesize these intricate ideas and connect the dots.
And all the curiosity, pulling out the surprising facts and making sure we really understand the aha moments behind these, let's face it, pretty dense concepts.
Yeah.
The sources we have are mapped for this journey, full of intriguing details and, well, some surprising insights. We're going to extract the most important nuggets of knowledge for you, our listener.
Yeah, we'll start with concepts that are actually confirmed. How speed and gravity bend time. Effects that are measurable and even used in technology today, giving us a one-way ticket, effectively, to the future.
Okay.
Then we'll venture into truly exotic theoretical territory, like warped space-time geometries and um, wormholes that might allow travel to the
That's
past.
the really weird stuff.
Exactly. We'll grapple with the mind-bending paradoxes these possibilities raise, explore some proposed resolutions for those paradoxes, and even touch on how the bizarre world of quantum mechanics is adding new, strange twists to the conversation and leading to some pretty surprising lab simulations.
Okay, let's unpack this. Sounds like quite a journey.
Let's do it.
So when we talk about time travel in physics, it's really not just a sci-fi trope dreamed up out of nowhere, is it? Our sources make it clear that the idea of time bending, of time flowing differently for different observers, it emerges naturally from Einstein's theories of relativity. But, and this seems like a big but, it requires some pretty extreme conditions compared to our everyday experience.
That's absolutely right. The journey really begins with special relativity, Einstein's theory from 1905, which deals with motion, especially at high speeds. And the core idea here is called time dilation.
Time dilation. Okay, I've heard that term. That's the thing where a clock that's moving ticks slower than a clock that's standing still, right? As seen by the stationary observer.
Precisely, yeah. Imagine you're on a spaceship traveling very, very fast, maybe a significant fraction of the speed of light, while I'm back here on Earth.
Okay.
From my perspective, watching you zoom away, your clock on the spaceship is literally ticking slower than mine here on Earth. Your time is actually passing more slowly relative to mine.
So if I traveled at near light speed for what felt like, I don't know, maybe a few years to me, and then I turned around and came back to Earth, I would have experienced much less time passing than everyone I left behind.
Yep.
Maybe decades or even centuries could have gone by on Earth while only a few years passed for me.
Mhm.
So I've effectively traveled into their future.
That's it, exactly. It's a genuine, though perhaps not intuitively obvious, form of time travel into the future predicted directly by special relativity. And the faster you go, the more pronounced this time dilation effect becomes.
Okay, okay. And then we add general relativity, Einstein's theory from, 1915, which brings gravity into the picture. How does gravity affect the flow of time?
Well, general relativity fundamentally describes gravity not as a force pulling objects together, but as a curvature of space-time itself caused by mass and energy.
Right, the whole fabric of space-time being warped.
Precisely. And this curvature, this warping of space-time, also causes time dilation. It turns out clocks run slower in stronger gravitational fields.
So if I were somehow standing on the surface of a supermassive object, like a neutron star or near a black hole's event horizon, time would pass dramatically more slowly for me than for someone far away in weak gravity.
Dramatically, yeah.
And even just closer to Earth's surface compared to high up in orbit,
Right.
there's a small difference.
Correct. There is. The closer you are to a massive object, the stronger the gravitational field, and the slower time passes for you relative to someone experiencing weaker gravity further away. It's another distinct way time can dilate based on your location in the spacetime fabric.
Okay, so we have time dilation due to speed, that's special relativity, and time dilation due to gravity general relativity. Now, here's where it gets really interesting for me, and maybe one of the most surprising facts from our sources for people who think this is all just theoretical physics mumbo-jumbo.
Go on.
These effects aren't just blackboard equations or abstract concepts. They are real, measurable, and confirmed effects. This isn't speculation.
They absolutely are. That's a critical point. The sources specifically mention the Galileo navigation satellites orbiting Earth right now. This isn't some theoretical thought experiment about the distant future. It's real technology that works because we account for these effects.
Okay, tell us more about those satellites. How do they provide concrete proof of this time bending?
Right, so the Galileo satellites are part of a global navigation system, kind of like GPS. They carry incredibly precise atomic clocks on board.
Okay.
And because their orbits aren't perfectly circular, they actually experience varying gravitational fields depending on how far they are from Earth at any given moment. And their speed relative to a ground station also fluctuates.
Makes sense.
So the critical thing is that scientists and engineers have precisely measured the time shifts on these atomic clocks aboard the satellites compared to identical clocks on the ground.
And what did they find? Did it match Einstein?
It matched perfectly down to astonishing accuracy. They found exactly what Einstein's formulas predicted. The clocks on the satellites ran slower when they were closer to Earth. That's the gravitational time dilation you mentioned, because gravity is stronger closer to the Earth's surface.
Right.
And they also ran slower when the satellite was moving faster relative to the ground station. That's the velocity time dilation from special relativity.
Wow. Both effects measured separately.
Both distinct predicted time shifts, both measured and confirmed experimentally in the real world on operational satellites.
That's incredible.
Yeah.
It means that if you use GPS or any satellite navigation system today, it only works accurately because the software running it accounts for both gravitational and velocity time dilation predicted by relativity.
Exactly.
If we didn't incorporate Einstein's time-bending effects into the calculations, the position fixes would drift off very quickly, making the whole system useless within minutes or hours.
That's a crucial takeaway. These effects are not theoretical speculation about some far-fetched scenario. They are confirmed, everyday parts of how our universe works and how our essential modern technology functions. Time truly does pass at different rates for different observers, depending on their speed and the gravity they experience.
Okay, so special and general relativity show us that time can certainly flow differently, and by moving fast or being near strong gravity, you can definitely travel into the future relative to someone else who stayed put. It's a real thing.
Yes, absolutely. But this brings us to the limitation, and it's a big one. As our sources highlight, in their most straightforward application, special and general relativity imply primarily a one-way ticket into the future. Getting back to the past, well, that requires bending space-time in ways that are far more exotic, far more speculative than simply moving or sitting near a star.
Right, and this is where things get truly mind-bending and we venture deep into theoretical possibility. How does physics even conceive of a path or configuration in spacetime that would allow going back in time? That seems impossible.
Well, it requires manipulating the very fabric of spacetime itself, not just moving through it along a standard path. In general relativity, the core concept linked to the theoretical possibility of past time travel is something called a closed timelike curve, a CTC.
Okay, closed timelike curve. Let's break that down simply with just a regular timelike curve.
A timelike curve is basically just the path of an object as it moves through spacetime. Think of it like your trajectory, mapping your position in space and your progression through time from one moment to the next. For us right now, sitting here, our timelike curves are moving steadily forward into the future.
Makes sense. So a closed timelike curve, what does that mean?
A CTC is a world line, a path through spacetime that loops back on itself. Imagine your trajectory bending around somehow until it connects back to a point in spacetime it already passed through, but in the past.
Whoa.
The source puts it very clearly. If you could bend your timelike curve so that it looped back on itself, you have somehow traveled back in time. Your path ends up back at an earlier moment in your own history.
That still sounds purely like science fiction, like completely made up. But you're saying Einstein's equations, the very ones that describe gravity and space-time so accurately for things like GPS, they actually allow for these theoretically.
This is another one of those surprising facts from the sources. Yes, surprisingly, pure general relativity, in principle, does admit mathematical solutions that contain these CTCs. His equations don't inherently outlaw these time loops. They are, mathematically speaking, valid solutions to the equations describing how spacetime can be shaped by mass and energy.
Okay, my mind is slightly blown. What kind of bizarre space-time shapes or configurations are we talking about that contain these CTCs? Like, what would that even look like?
Well, there are a few famous theoretical examples that physicists have found over the years, really pushing the boundaries of what GR allows. Back in 1949, the brilliant mathematician Crete Gödel, who was actually a friend of Einstein's at Princeton, found an exact mathematical solution for a universe that is uniformly rotating.
A rotating universe.
Yeah, a theoretical model universe.
Yeah.
And in this Gödel universe, it turns out you could, in principle, travel in a sufficiently large circle and end up back where you started, but at an earlier time.
A whole rotating universe that allows global time travel just by going in a circle. That's wild to even imagine.
It is wild and probably not like our actual universe,
Uh-huh.
as there's no evidence our universe is rotating on a large scale in that particular way.
Okay, so maybe not that one. What else?
Another example comes from black hole physics, specifically the Kerr solution, which describes a rotating black hole, the kind we think actually exist.
Right.
Inside the ring singularity, the theoretical structure where the mass is concentrated in a spinning black hole, not a point like in a non-spinning one, very close to what's called the inner event horizon, the geometry of space-time is predicted by the equations to contain CTCs.
In the causal donut region, as one source vividly calls it, inside the black hole.
Exactly. Though it's crucial to note that this region inside a black hole is generally considered highly exotic and perhaps even unphysical, the conditions there are extreme, likely requiring physics beyond general relativity, like quantum gravity, to fully understand what's really going on.
Okay, so maybe not practically accessible. Any other ideas?
Well, other theoretical possibilities that mathematicians have explored include solutions like Frank Tipler's idea of an infinitely long, incredibly dense, spinning cylinder, or certain configurations of moving cosmic strings if those hypothetical objects exist. In principle, the intense gravity and rotation around these theoretical objects could also create conditions for CTCs.
So general relativity provides these theoretical blueprints for space-time shapes that could, mathematically, contain time loops, pathways back to the past. But there's always a catch, isn't there? These aren't exactly structures we see lying around the cosmos.
Absolutely. The catch is huge. While GR allows these solutions mathematically, they almost always require incredibly extreme conditions or configurations that we have no evidence of existing naturally in our universe in an accessible way. They often lie behind event horizons, like inside the Kerr black hole, making them inaccessible once formed. Or they demand unphysical properties like infinite length or density to exist or remain stable according to the classical theory. Our sources really emphasize that no known natural process is expected to produce these accessible configurations.
So allowed in theory by the math, yes. But the universe doesn't seem to build these kinds of time machines for us easily, if at all.
That seems to be the case based on what we know.
Okay, speaking of exotic geometries allowed by GR, wormholes are another concept often linked to time travel, popularized heavily in science fiction. Are those a real possibility in physics or just fiction?
Wormholes are also theoretical constructs that emerge from general relativity, much like the idea of CTCs. You can think of them, very simply, as tunnel-like shortcuts connecting distant regions of spacetime.
A tunnel through space-time.
Yeah, the idea is they could potentially connect two points very far apart in space, acting as a shortcut, or even potentially connect two different points in time.
Like a cosmic shortcut, maybe through a different dimension or something. That's how they show it in movies.
That's the common visualization, yeah. In the simplest theoretical type, sometimes called an Einstein-Rosen bridge, they're actually non-traversable.
Non-traversable, why?
They would likely pinch off or collapse too quickly, faster than even light could get through, so nothing macroscopic could actually pass from one end to the other.
Okay. So not very useful for actual travel then. Kind of a dead end, theoretically.
The simple ones, yes.
Hmm.
But then came some really groundbreaking theoretical work by physicists like Kip Thorne and his colleagues Michael Morris and Ulvi Yurtsever back in the late 1980s. They showed that, in principle, a highly advanced civilization could potentially enlarge and stabilize a wormhole and even convert it into a time machine.
Okay, now that sounds like the sci-fi version kicking in. How would you theoretically turn a space tunnel into a time machine? That seems like a huge leap.
Well, the theoretical mechanism they proposed involves taking a traversable wormhole, one that you've somehow managed to hold open, which is a big if, and creating a significant time differential between its two mouths or openings.
How would you do that?
You could do this by, for example, keeping one mouth stationary, maybe near Earth, while you take the other mouth on a journey at a significant fraction of the speed of light.
Using that time dilation effect we talked about earlier from special relativity,
Yeah.
because the moving mouth ages slower.
Precisely. The mouth that moved at high speed would experience less time passing than the stationary mouth, relative to some outside observer. Once you stop moving it and bring it back nearby, the two mouths would still be linked by the wormhole tunnel, but they would be out of sync in time. There would be a permanent time offset between the two ends of the tunnel.
So if I stepped into the mouth of the wormhole that stayed put, which might be, say, here on Earth today, I could theoretically come out the other mouth, the one that traveled fast and returned, and find myself in the past relative to when I entered.
That's the theoretical idea, yes. Passing through the wormhole would then send you to a different time, either the past or the future, depending on which mouth you entered, and the direction of the time offset relative to your starting point outside the wormhole. Our sources even reference an artist's concept illustration showing a spacecraft using a wormhole like this, highlighting this theoretical potential.
Okay, but there's still a major requirement to make this work, beyond just having a wormhole in the first place, right? You mentioned keeping that wormhole open and stable. That sounds like a problem.
Yes, this is the critical, really exotic requirement identified by Thorne and his colleagues. To hold a wormhole open against the massive pull of gravity and prevent it from collapsing instantly, it needs to be propped open by a type of material or energy distribution with very strange properties. Specifically, they figured out it needs exotic matter that possesses negative energy density.
Negative energy density, what is that?
Well, it's not your everyday matter, which has positive mass and positive energy. Negative energy density is a concept where, roughly speaking, the energy in a region of space is less than zero, less than empty space. It's highly theoretical, something we don't have readily available, and we don't really know how to create or handle it in large quantities, if it even exists in the necessary stable form and scale.
So wormholes could theoretically lead to time travel to the past, but they rely on being stable, which requires this mysterious, possibly non-existent exotic matter with negative energy. That sounds like a pretty big hurdle.
It's arguably the biggest physical hurdle for traversable wormholes, yes.
Huh.
And crucially, our sources point out that a traversable wormhole configured in this way as a time machine would inherently lead to closed time-like curves, those time loops we just discussed.
So it connects back.
Exactly. Wormholes are just one potential theoretical mechanism, one possible space-time configuration that could theoretically create the conditions for those CTCs to exist and potentially be accessed.
This all sounds incredibly fascinating from a purely physics perspective, exploring what the equations allow, even if it's extreme. But it immediately brings up the major hurdle that makes most people, myself included sometimes, just dismiss time travel as completely impossible: the paradoxes.
The paradoxes are indeed the elephant in the room. They're the seemingly insurmountable logical challenge. While general relativity in principle allows for spacetime configurations like CTCs and theoretical time machines like wormholes, these possibilities immediately raise very famous, very problematic logical contradictions that seem to break causality itself.
The classic one, of course, the one everyone knows, is the grandfather paradox.
Right. Lay it out for us. How does it work?
Well, it's the scenario where you travel back in time and you do something that prevents your own existence. The most common example is going back and somehow preventing your grandparents from ever meeting. Maybe you, I don't know, accidentally cause one of them to miss the train where they were supposed to meet, or something worse,
Okay.
which means your parent is never born, which means you are never born.
And if you were never born, you couldn't have traveled back in time in the first place to prevent your grandparents from meeting and thus prevent your own birth.
Exactly. It's a devastating logical loop.
Right.
It just seems to break causality in a fundamental way. How can something cause an event that then prevents its own cause from ever happening? It feels like it makes unrestricted time travel just logically impossible.
And it raises weird questions about free will, too, right? If our actions could erase the conditions that allowed us to act.
That's the core, inescapable contradiction posed by the grandfather paradox. It's a powerful argument against the possibility, or at least the unrestricted possibility, of backward time travel. And there's another famous one, slightly different in nature, called the bootstrap paradox, sometimes called the ontological paradox.
What's that one about? It sounds less destructive. This one involves information or objects that seem to exist within the time loop without having any external origin point. Our sources give a classic example. Imagine you travel back in time, and you take with you a physics textbook. Maybe the very textbook that you use to learn everything you know about physics.
Okay, got my textbook.
You go back to, say, 1950, and for some reason you give this exact textbook, word for word, to your younger self, or maybe to a budding young physicist who will eventually become your professor or mentor.
Yeah, right.
Your younger self, or this teacher, then uses this book, which contains future knowledge they didn't discover themselves, to become a great physicist. They learn everything in it, absorb it all, and eventually they grow up to write the very same physics textbook that you took back in time in the first place.
Oh, wait.
The book then gets published in the future, exists for you to find it, learn from it, and then take it back in time to give it to them.
So, where did the information in the book come from initially? It wasn't created at any point outside the loop. It just seemed to exist because the loop exists. It's like a self-generating piece of information or object with no clear starting point.
Precisely. The book exists, the knowledge exists, but it has no ultimate source outside of the time loop itself. It's a different kind of paradox, not necessarily destroying existence like the grandfather paradox, but raising profound questions about the origin of information or physical objects within a time loop. It seems to violate our intuitive sense that things must, well, originate somewhere.
So these paradoxes are the big problem. If physics allows for these potential time travel structures like CTCs and wormholes, how do physicists grapple with these seemingly impossible logical scenarios? Do they just throw their hands up and say, well, guess time travel is impossible then?
Not at all, actually. That's where physicists have proposed several potential resolutions. The thinking isn't necessarily to say time travel is impossible because of paradoxes, but rather to explore if the laws of physics themselves, if they allow time travel, might also contain inherent mechanisms that prevent paradoxes from ever occurring, or perhaps resolve them in unexpected ways.
Okay, I'm intrigued. Let's hear some of these proposed solutions. How might the universe prevent or handle a grandfather paradox if I tried to cause one?
Well, which the earliest and most influential ideas, dating back to the 1980s, so predating some of the more recent quantum ideas we'll get to, is Igor Novikov's self-consistency principle.
Novikov's self-consistency principle. What does that say?
It essentially asserts that only globally consistent histories can occur. In any time travel scenario involving a CTC, events must conspire, naturally, within the laws of physics, in such a way that paradoxical outcomes simply never happen. Contradictory events, like successfully preventing your own birth, are assigned zero probability of occurring within a time loop.
So if I traveled back in time, specifically intending to stop my grandparents from meeting, according to Novikov, something would inevitably happen to prevent me from succeeding. Like maybe I trip on a conveniently placed banana peel at the crucial moment, or my time machine breaks down just before I get there, or I just have a sudden, inexplicable change of heart and decide, nah, maybe not. The universe somehow forces a consistent outcome.
According to Novikov's principle, yes. The laws of physics operating within that time loop would somehow conspire to ensure that the attempted paradox fails. The Universe Today source we looked at explicitly states that Novikov's principle guarantees a paradox-free solution to any situation. It doesn't necessarily mean you can't travel to the past. It just means that whatever you do in the past must ultimately be consistent with the history that already happened to allow you to travel in the first place.
It forces the time loop to close in a way that makes logical sense within the overall history. So the bootstrap paradox with the textbook isn't necessarily forbidden then. It's just that the loop is the history. I give the book to my younger self because that's always how my younger self got the book in that specific self-consistent timeline. The origin isn't outside the loop, it's in the loop itself, self-contained.
Exactly. The time travel event enables the self-causing effect, but every event closes the loop in a way that was always true from the start in that particular history. What's interesting, though, and mentioned in some recent theoretical work by Tobar and Costa in 2020 that our sources flagged, is that even if a CTC forces certain fundamental consistency conditions, like, say, ensuring your parents meet, if that's part of the necessary chain of events for the time traveler to exist and make the trip the rest of the system.
Like my other actions.
Yeah, your other actions and choices within that consistent framework might still be able to evolve in many possible ways. This suggests some degree of free will might still remain, even within a self-consistent time loop. You're constrained from creating a paradox, but maybe not completely predetermined in every detail.
That's a very subtle but important distinction. It's not necessarily total predetermination, just a strong constraint towards a globally consistent outcome. Okay, another proposed resolution often heard, especially in popular discussions, is the many worlds interpretation, or the idea of parallel timelines splitting off.
Right, this idea is frequently invoked. It often stems from interpretations of quantum mechanics, although it's applied more broadly here in the context of time travel paradoxes. The suggestion is that a time travel event, or any action you take in the past that would cause a paradox in your original history, doesn't actually alter that original timeline. Instead, it causes reality to branch, or it effectively moves you into a new parallel timeline or universe.
So if I go back to try and stop my grandparents from meeting, I don't affect the timeline I came from where I was born and had grandparents who met. Instead, by taking that action, I just create or enter a new branch of reality where they don't meet, and now I exist in that new branch, having arrived from a different history where they did meet.
Yes, that's the core idea. In this view, you might succeed in preventing their meeting in the new timeline or branch you've entered, and in that new history, your grandparents might not have met. But you, the time traveler, originated from a different timeline where your grandparents did meet, which is why you existed in the first place and were able to make the trip.
Ah, I see.
Therefore, there's no logical contradiction for your own existence because your origin is rooted in a different history. The paradox is avoided by simply shunting the time traveler and their paradoxical actions off into a separate reality.
Okay, that neatly sidesteps the grandfather paradox, but it does come with the rather large requirement of believing in these constantly branching or parallel universes, which is a whole other and quite speculative can of worms, isn't it?
It is
It relies on a specific interpretation of quantum mechanics, rather than being a strict consequence of classical general relativity itself.
exactly. It's philosophically neat for paradoxes, but physically demanding in terms of ontology. Now, a maybe theoretical challenge to time travel coming more directly from the context of general relativity, and perhaps the most widely cited proposed resolution for paradoxes among theoretical physicists working in gravity, is Stephen Hawking's chronology-protection conjecture.
Ah, Hawking, of course.
Yeah.
What was his idea regarding paradoxes in time travel?
Hawking conjectured quite strongly that there must be some deep fundamental physical mechanism, most likely involving effects from a complete theory of quantum gravity that we don't yet fully understand, that actually forbids any closed time-like curve from forming in the first place, at least on macroscopic scales accessible to observers.
So nature itself has a fundamental law against time travel to the past. It just won't allow it.
That's the core idea. Nature protects history from paradoxes by making time travel inherently impossible. His conjecture is that any attempt to actually create a time machine, whether it's building Tipler's rotating cylinder, manipulating a wormhole, or whatever the proposed mechanism might be, would somehow become unstable as it approached the critical point where a time loop could actually form.
How would it become unstable?
Hawking suggested it might lead to uncontrolled energy buildup, perhaps quantum vacuum fluctuations becoming infinite near the potential CTC boundary, or maybe a catastrophic gravitational collapse before the time loop could actually close and allow travel to the past. Basically, the physics breaks down before the time machine can be completed or used.
He put it quite clearly and famously, didn't he?
Yeah.
Something like, the laws of physics do not allow the appearance of closed time-like curves.
Yes, he did. He was quite firm on this. Now, this conjecture remains unproven because, as I said, we don't yet have that complete working theory of quantum gravity that smoothly unites relativity and quantum mechanics. But it's strongly supported by many semi-classical analyses. These are calculations that combine the framework of general relativity with some basic concepts from quantum field theory. And these analyses often find mathematical divergences, essentially infinities appearing, precisely at the space-time boundaries where time loops might otherwise form.
Suggesting quantum effects would prevent their creation.
Exactly. It suggests quantum effects would likely intervene and destroy the potential time machine. So, while it's still technically a conjecture, it strongly suggests that paradoxes are avoided because the fundamental laws of physics might simply make travel to the past impossible in a complete theory.
It's like the universe has a built-in, maybe quantum-level safety mechanism against paradoxes, rather than needing complex logical rules like Novikov's to resolve them after they theoretically happen.
That's a really good way to think about it. It avoids the problem entirely by preventing the conditions necessary for paradoxes from ever arising on macroscopic scales. And interestingly, very recent theoretical work is exploring similar ideas but from a slightly different angle, potentially operating within the time loop itself, if one could form.
Oh,
The sources mention research by Germain Gavasino, published very recently in 2025, proposing a kind of quantum self-correction mechanism that could operate inside a CTC.
quantum self-correction
Mm.
within the loop. What does that mean exactly?
It suggests that if a CTC were somehow present, it might possess an internal mechanism, perhaps leveraging the bizarre rules of quantum mechanics and things like quantum fluctuations to automatically enforce consistency from within. Gavasino's work specifically argues that entropy, that measure of disorder that normally always increases according to the second law of thermodynamics, defining the arrow of time,
The uptimes arrow?
that entropy could actually locally decrease within the CTC.
Decrease. That sounds like going against a fundamental law.
It does, and it's very counterintuitive. But the idea is that this local decrease in entropy would happen precisely in a way needed to undo or counteract any changes that would lead to an impossible paradox, thus keeping the overall evolution unitary, probability preserving, and globally consistent.
So the physics inside the time loop would automatically adjust itself in this really strange way, maybe violating the usual arrow of time locally, just to ensure a consistent outcome comes out the other end.
That's the hypothesis presented in this very recent work. The source describes this view as the universe automatically correcting the scenario if you tried to create a paradox while inside a CTC, adjusting the local physics so the final state remains logically consistent and avoids a permanent contradiction.
So rather than Hawking preventing the loop from forming, this idea suggests the loop itself might have a consistency mechanism baked in, perhaps enabled by quantum effects, which ensures any attempt in paradoxes just fizzle out or correct themselves.
That's the essence of this newer proposal, yeah.
Okay.
Pushing the frontier of these theoretical ideas. It's another potential way the universe might reconcile the theoretical possibility of time loops with the absolute requirement for logical consistency.
Okay, let's try to synthesize this part on paradoxes and resolutions, because there are quite a few ideas floating around.
Yeah.
It seems the paradoxes aren't necessarily seen by physicists as definitive proof that time travel is impossible,
Right.
but rather as a strong indication that if time travel is possible, the universe's laws must somehow enforce self-consistency. Is that fair?
I think that's a very fair summary. Paradoxes are currently only thought experiments that arise when we explore the logical consequences of general relativity solutions that contain CTCs. If time travel were ever actually realized in our universe, the most likely outcome, based on these proposed resolutions, is that any attempt at a paradoxical outcome would simply have zero chance of happening, as Novikov suggested. Or it would be resolved by complex quantum effects, maybe quantum self-correction, or perhaps by branching timelines if you subscribe to that view. The point is, the universe or the time loop structure itself would somehow enforce consistency. The paradoxes highlight the absolute need for physics to remain self-consistent, even in the presence of these exotic theoretical structures.
Okay, and this brings us neatly to how quantum mechanics itself is adding new, strange layers to this whole discussion, moving beyond just classical relativity space-time geometry.
Indeed. While classical general relativity gives us the basic framework for potentially bending space-time into loops, quantum mechanics, the physics of the very small, has its own fundamental rules for how systems evolve over time. And normally, quantum theory describes systems evolving unitarily forward in time, a predictable, probability-preserving step-by-step progression.
But theorists have found ways quantum mechanics might accommodate the idea of time loops, or CTCs. How does that work?
Yes. Building on that core concept of consistency principles, theorists have explored how quantum systems themselves might behave if they were allowed to enter a CTC. David Deutsch, back in 1991, created one of the earliest and most influential quantum models for CTCs.
Okay, Deutsch. How did he approach it quantumly?
He formulated a model where quantum systems could evolve along a closed, timelike curve by imposing a specific mathematical requirement for consistency on the system's state. This state is described by something called a density matrix, which basically captures all the possible outcomes and their probabilities for a quantum system.
Right.
His model demonstrates how quantum mechanics, by leveraging specifically quantum concepts like superposition, the ability of a quantum particle to exist in multiple states simultaneously until it's measured, could potentially resolve classical paradoxes. And arguably, it could do this without necessarily needing to invoke those branching parallel universes we discussed earlier.
Also,
The idea is that the different, seemingly contradictory possibilities involved in a paradox, like being born versus not being born, could somehow coexist in a quantum superposition within the loop, leading to a consistent overall outcome when viewed globally, averaged over all possibility.
Okay, that's definitely complex, but the core idea is that quantum weirdness, like superposition, might provide a mathematical way to resolve the logical contradictions internally within the time loop's physics itself. It allows for possibilities that classical logic forbids.
That's the essence of it, yes. The bizarre rules of quantum mechanics offer potential theoretical loopholes for maintaining consistency, even in these extreme situations. And the sources mention another influential quantum model related to this, post-selected CTCs, or PCTCs.
PCTCs. Okay, what's that?
Yes, this was proposed by Seth Lloyd and colleagues around 2011. This model uses entangled qubits, those quantum particles whose fates are mysteriously linked no matter how far apart they are, in a technique called post-selection.
Entanglement and post-selection.
hmm
What's post-selection?
Post-selection is a method used in quantum information experiments where you essentially only consider the experimental outcomes. You only keep the data, where a measurement on one part of your quantum system yields a specific predetermined result that you were looking for. You kind of throw away the runs where you didn't get the result you wanted on that measurement.
Okay, so how does using entangled particles and picking only certain outcomes create an effective channel to the past? That sounds like cheating.
It does seem a bit like that. The core idea involves preparing two particles in a maximally entangled state. You then interact one of the particles, let's call it qubit A, with something, say, a theoretical event or maybe a bit of information you want to influence or measure that represents something in the past, part of your simulated loop. Then, crucially, you measure the second entangled particle, qubit B, at a later time, and you post-select for a specific predetermined outcome of that measurement on B. The strange result, predicted by the math and seen in simulations, is that the state you find qubit B seems to retroactively influence the state of qubit A at the earlier time when it interacted with the past event.
Whoa. It sounds like the outcome of a future measurement seems to affect or determine a past state of its entangled partner. That feels incredibly counterintuitive, like sending information backward in time somehow.
It absolutely does feel like that, and that's precisely why it's used to model time travel analogs or simulations. The sources describe this as yielding a noiseless retrocausal connection, meaning it looks like you're influencing the past cleanly without the usual noise or uncertainty you'd expect.
Okay.
But they also emphasize it's designed mathematically to always produce self-consistent results. Instead of leading to classical paradoxes like the grandfather paradox in this PCTC model, the paradoxes become input filtering problems.
Input filtering, what does that mean?
What that means is that inconsistent initial conditions or inputs for the qubits combinations that would lead to a paradox if allowed are simply filtered out or made impossible by the post-selection process itself. The mathematical framework just doesn't allow those inconsistent inputs to survive the post-selection condition required to complete the loop. So the outcomes you measure are always consistent with what must have happened earlier in the simulated loop.
So the quantum setup effectively filters out the possibilities that would lead to a paradox, like a quantum spam filter for contradictions built into the entanglement and post-selection rules.
That's a pretty good analogy, actually, yes.
Sure.
The constraints of entanglement and the post-selection process ensure that only consistent possibilities are observed in these models. And fascinatingly, these aren't just abstract mathematical models anymore. Physicists are actually trying to simulate aspects of these ideas in the lab.
That's amazing. People are experimenting with simulated time travel. The source mentions an experiment from 2023 by Arvidsson Schuker, Halpern, and colleagues. They described a scheme to probabilistically improve one's past choice. What does that experiment actually demonstrate? What do they do?
Right, so they used entangled photons, particles of light, and circuits based on quantum teleportation, which is another really bizarre quantum phenomenon related to entanglement. The experiment showed that by performing a specific measurement on one photon of an entangled pair after a measurement had already been performed on its partner photon.
Okay, so measure A, then later measure B.
Exactly. They showed they could effectively retroactively influence the optimal outcome or the probability distribution of that prior measurement on the first photon, A, based on the result they got from the later measurement on its entangled partner, B. It's like using a quantum trick to effectively bias the past result towards a more favorable outcome from the perspective of a future measurement on its entangled twin.
That sounds truly mind-bending. influencing an outcome after it's already technically happened, even just probabilistically shifting the odds.
It does, and it really taps into the strange, non-local correlations that are possible with entanglement. It's not changing the past deterministically, but influencing the probabilities associated with past events via future actions on an entangled system. And there was another recent experiment from Cater Murch and colleagues in 2024 where they built what they called a time-traveling quantum sensor.
A quantum sensor that travels through time. Now that sounds straight out of Star Trek.
Huh?
Are they sending sensors back?
Not physical travel, no. It's an effective simulation, again, using similar principles. They built a sensor using two entangled qubits. One qubit, the probe, was used to measure something that happened at a specific point in time in their experiment. It interacted with magnetic field representing the event in time.
Okay.
The second qubit, the ancilla, was measured later. The key finding was that measuring the ancilla effectively sent information about its state back in time via the entanglement link to the probe qubit at the earlier time.
How did that help?
This retroactive information transfer actually boosted the precision of the probe's initial measurement of the magnetic field. It made the sensor more accurate about the past event.
So, using the second qubit, measured later, allowed them to get more accurate information about what the first qubit experienced earlier. That's really clever.
Exactly. It's a way to improve a measurement or gain more information about a past event using information from a seemingly later point in the entangled system's evolution. It simulates an information flow that looks like going backward in time within the controlled quantum system, leading to a practical benefit better sensing.
These experiments sound revolutionary, mimicking aspects of time travel in the lab. But it's crucial, as our sources really emphasize, to understand what they do not do. They are not evidence of macroscopic time travel for people or objects.
Absolutely not. Our sources are very clear, and this is a critical caveat. These experiments do not truly violate causality in the classical sense, where a cause must always precede its effect in our everyday world. No information is being sent to the distant macroscopic past beyond what the fundamental limits of quantum mechanics and uncertainty allow.
Okay.
They are best seen as powerful simulations or analogs of time travel scenarios. They use the weirdness of entanglement and post-selection to mimic certain mathematical aspects of time loops and retrocausality in a carefully controlled laboratory setting. But crucially, they do this without actually breaking the fundamental causality of our universe on macroscopic scales.
Right. The source directly clarifies this critical distinction, saying something like, whether closed time-like curves exist in reality, we don't know the laws of physics that we know of allow for the existence of CTCs, but those laws are incomplete because they lack quantum gravity. One can use entanglement to simulate CTCs.
That quote perfectly captures the state of play. We can simulate the mathematical structures and the strange behaviors associated with time loops in the quantum realm, and these simulations show how consistency might be enforced quantum mechanically. But that's fundamentally distinct from proving that macroscopic time travel into the past is possible in the real universe. That possibility seems intimately tied up with our understanding, or lack thereof, of a full theory of quantum gravity.
Which brings us right to the cutting edge of modern physics research. How do these time travel ideas connect with the biggest unanswered questions in physics, like finding that elusive theory of quantum gravity that can unite Einstein's relativity with quantum mechanics?
This is where things get truly speculative and, frankly, incredibly exciting. Concepts like wormholes are being explored not just as theoretical shortcuts in classical GR, but increasingly in the context of quantum gravity theories, particularly those attempting to unify quantum mechanics and gravity. For example, there's the fascinating EPR conjecture.
ER. EPR. Okay, that sounds like two very famous sets of initials from physics linked together. Einstein-Rosen and Einstein-Podolsky-Rosen.
Exactly. It links Einstein-Rosen bridges, ER, those simple theoretical wormholes we talked about, with Einstein-Podolsky-Rosen entanglement, EPR, the famous description of quantum entanglement, or spooky action at a distance.
Right.
The conjecture, famously championed by physicists like Leonard Susskind and Juan Maldacena, suggests quite radically that two black holes that are entangled with each other might actually be connected by a wormhole.
Wait, what? So spooky action at a distance and entanglement and spacetime tunnels, wormholes, might be two descriptions of the same underlying physical reality. That's mind-bending.
It's an incredibly audacious and profound idea, suggesting a deep fundamental connection between quantum information, entanglement, and the geometry of spacetime. wormholes. And physicists are actively using this conjecture in theoretical frameworks, like the AD-SCFT correspondence, to explore how quantum mechanics and gravity intertwine at their deepest levels.
At SCFT. That's the holographic principle idea, right? Gravity in a volume is like quantum theory on the surface.
Loosely speaking, yes. And within this theoretical framework, back in 2017, physicists Ping Gao, Daniel Jafferis, and Aaron Wall used this ER-EPR idea to construct a theoretically traversable wormhole. Not an error universe, mind you, but in a specific type of theoretical spacetime called anti-de Sitter space, ADS, which is often used as a theoretical laboratory for quantum gravity.
How did they manage to make it traversable, even in this theoretical model? Didn't we say you need exotic matter?
They did it by coupling two entangled black holes in this theoretical ADS space and then carefully tuning a specific quantum interaction between them, something highly technical called a double trace deformation. This specific quantum interaction effectively gave the wormhole throat an averaged negative quantum energy, which is precisely the kind of exotic stuff theoretically needed to prop it open, at least briefly, allowing something to pass through in the model.
So quantum mechanics itself, via entanglement and specific interactions between quantum systems, might potentially provide the exotic matter needed for a traversable wormhole, at least in these specific theoretical contexts.
Potentially, yes, in these highly theoretical models that explore the boundaries of quantum gravity. However, and again, this is crucial, even this theoretically traversable quantum wormhole constructed using ER-EPR cannot be used to send signals to the past within the model. It only allows the safe transfer of quantum information between the two entangled black holes, respecting causality. No time machine resulted.
Interesting. So even at the cutting edge of trying to unify gravity and quantum mechanics, causality seems stubbornly protected. The wormhole might become traversable, but not for time travel.
That's what these particular holographic results suggest. They hint that quantum effects might allow for exotic spacetime structures like traversable wormholes without necessarily enabling paradoxical time loops or violating causality. Researchers are studying various related ideas like eternal wormholes or world-sheet wormholes in high-energy theory to explore how quantum gravity could potentially allow shortcuts in space-time while still fundamentally avoiding paradoxes. It's a very active area.
And returning briefly to paradox resolutions, that very recent work by Gavesino linking time travel and entropy that falls squarely into this frontier too, right? It suggests if a CTC exists, maybe quantum gravity effects allow it to automatically fix itself thermodynamically.
Yes, exactly. That work links the potential presence of CTCs directly to the second law of thermodynamics and the arrow of time, suggesting a deep connection that might be governed by quantum gravity. Gavesino's finding, as we discussed, suggests that if a CTC were present, the strange physics inside it could enforce consistency by allowing entropy to locally decrease within the loop itself.
Like the time loop, automatically tidying up any paradoxical thermodynamic mess, ensuring things flow consistently overall, maybe preserving the second law globally, even if it's bent locally.
That's one way to interpret it, yes. It implies any time loop might automatically repair local violations of the second law, preserving a consistent thermodynamic arrow of time globally, even if things get weird inside the loop. It's a fascinating theoretical idea about how fundamental physical laws might self-correct in these extreme space-time conditions predicted by GR, but potentially governed by quantum gravity.
So even if you could travel back, you might find yourself unable to make changes that fundamentally violate deep physical principles, like the overall increase of entropy on large scales. The universe fights back.
That's one possible implication being explored. And finally, looping back one more time, Stephen Hawking's chronology-protection conjecture remains a major guiding principle and point of research. Has a definitive mechanism been found yet? Maybe from string theory or loop quantum gravity that definitively blocks all possible CTCs on all scales? No, not yet. It remains an open problem at the forefront of theoretical physics. As we mentioned, semi-classical analyses often find those mathematical divergences appearing precisely where time loops might form, strongly supporting Hawking's idea that quantum effects would likely destroy a nascent time machine before it could become operational. But a complete, rigorous proof from a universally accepted full theory of quantum gravity is still missing, simply because we don't have that full theory yet.
What about on a very small microscopic scale? Could quantum mechanics allow tiny violations of strict chronology, even if macroscopic time machines are forbidden?
That's an interesting point some physicists, like Gad Glampadakis and others mentioned in the sources, have raised. They've noted that on very microscopic scales, the quantum realm, the strict classical notion of chronology, might not hold absolutely. There could potentially be tiny probability amplitudes, that's a concept from quantum mechanics, related to the likelihood of different outcomes happening, for effects that look like tiny, fleeting time loops or subtle violations of strict cause and effect ordering on very, very small distance and timescales.
So maybe not a time machine for a person or even a message, but perhaps quantum particles or fundamental events behaving in ways that hint at backward causality, or tiny virtual loops as part of the quantum foam of spacetime.
It's a theoretical possibility being explored at the intersection of quantum field theory and gravity. It means the jury is still out on whether a full theory of quantum gravity ultimately enforces absolute chronology protection and forbids time travel entirely, or perhaps allows it only in extremely limited ways, possibly only on microscopic scales, enabled by the inherent fuzziness and strange rules of quantum mechanics, while still preventing macroscopic paradoxes.
Wow. Okay. We have covered a lot of ground in this deep dive, moving from confirmed reality all the way to the most speculative frontiers of theoretical physics. So, after diving into all these sources, what's the present state of the science regarding time travel? Where do we actually stand right now?
Well, the summary that emerges pretty clearly from our sources is this. Modern physics, as we currently understand it, neither guarantees nor fully excludes the possibility of time travel to the past. The door isn't slammed shut, but it's certainly not wide open either.
Right. Relativity shows us how time can bend with speed and gravity, giving us that confirmed one-way trip to the future, which is amazing in itself. And theoretically, it allows for these mind-bending space-time geometries like CTCs and wormholes that could mathematically enable travel to the past.
But the conditions required for those structures seem incredibly extreme, often unphysical based on what we observe and understand about the universe today, or hidden behind event horizons.
And the quantum mechanics adds its own strange layer. It provides theoretical frameworks like Deutsch's model and post-selected CTCs, and even inspires these experimental simulations that emulate certain aspects of time loops and retrocausality using entanglement and post-selection in the lab, showing how consistency might work quantumly.
Yes, but the really striking pattern, I think, that emerges from nearly every serious theoretical model developed so far, whether classical or quantum, is that if time travel were possible, the universe's fundamental laws seem poised to avoid the paradoxes by imposing some kind of internal consistency rule.
Yeah, that came up again and again. Whether it's Novikov's principle saying inconsistent events just have zero probability,
Or the many worlds interpretation conveniently branching history off.
or Hawking's conjecture proposing nature prevents the loops entirely via quantum gravity effects.
Or even these newer ideas about quantum self-correction or thermodynamic consistency happening within the CTCs themselves.
The theoretical physics seems to strongly lean towards a paradox-free reality, even if time travel were somehow possible in some restricted form. Consistency is king.
That seems to be the unavoidable conclusion from the physics. And of course, perhaps most importantly in terms of practical, observable evidence in the real universe.
Yeah, what have we actually seen?
Zero. Absolutely nothing. No experiment has ever actually produced a functional time machine capable of sending a macroscopic object like a person, or even a single atom, verifiably back in time. And crucially, no paradoxical outcome predicted by these wilder theories like meeting a version of yourself from the future or observing an object like that bootstrap textbook appearing seemingly from nowhere has ever been observed in reality. The universe, as far as we can tell, appears stubbornly consistent and forward-moving on all macroscopic scales we can probe.
So the current research seems to strongly suggest that if time travel to the past is ever possible in the real universe, its mechanism is likely tied up in the deepest mysteries of quantum gravity, the theory we don't have yet. And whatever that mechanism is, it must adhere to strict self-consistency requirements, avoiding paradoxes at all costs.
That seems to be the overwhelming consensus from the material we explored today. The door isn't completely closed by known physics, but the path through it, if one exists at all, appears guarded by the fundamental need for consistency and likely requires physics beyond our current full grasp.
Wow. Well, we have covered such incredible ground in this deep dive. I feel like my brain has been stretched in a few different temporal directions, from the confirmed, everyday time-bending effects of speed and gravity that already send us effectively into the future.
To the truly theoretical, mind-warping possibilities of bending space-time itself into closed time-like curves and traversable wormholes for potentially reaching the past.
And grappling with that fundamental challenge of paradoxes, along with the really elegant and sometimes deeply strange proposed solutions emerging from both classical relativity and the quantum realm.
Unpacking these sources really gives us such a fascinating glimpse into the cutting edge of physics, doesn't it?
Ah,
And how scientists grapple with concepts that feel like they belong solely in science fiction novels. Hopefully you, our listener, now have the key nuggets of knowledge to understand what the science actually says about time travel, its daunting challenges, but also its tantalizing theoretical possibilities.
it's definitely a field that constantly pushes the boundaries of what we think is possible and forces us to question our most basic assumptions about the very nature of time, space, and causality. It makes you think.
And it leaves you with a question that really lingers, I think. Given that current physics seems to suggest any potential time travel must inherently be paradox-free, does that imply that history is fundamentally set in stone?
Mhm.
Is everything unavoidable even if you could travel through time because consistency must be maintained?
Or could the quantum realm, with its inherent fuzziness, its probabilistic nature, and its strange non-local connections, maybe allow just enough wiggle room on the microscopic scale to fundamentally challenge our classical ideas of a fixed past and future entirely?
It seems the ultimate question of time travel isn't just about building a machine, is it? It's about truly understanding the fundamental nature of reality itself at its deepest quantum gravitational levels.
A perfect thought to ponder after this journey into the possibilities and paradoxes of time. Absolutely. Well, thank you so much for joining us on this deep dive into the truly fascinating world of theoretical time travel.
It was a pleasure exploring these complex and mind-bending ideas with you.